Welcome to the deep dive. Today we're jumping into, well, the really intricate world of chemical equilibrium.
Yeah, specifically focusing on acid-base reactions and solubility. It's fascinating stuff.
Right. Our mission, as always, is to take complex ideas, this time from sources like chemistry, atoms first, and some related lecture notes.
And really boil them down for you.
Exactly. Distill them into the key insights you need. Think of it as getting you straight to the heart of how these chemical reactions actually work.
And these aren't just abstract concepts, are they? They're happening all around us.
Oh, definitely.
I mean, how your blood stays at the right pH, that's buffers, which we'll get into. Or even, unfortunately, how kidney stones might form.
Right, solubility comes into play there.
Yeah, and designing materials too. It's all about understanding how systems react when you, well, nudge them a bit.
Okay, let's start there then. Equilibrium. This idea of a perfectly balanced chemical system.
Uh-huh.
What happens when you disturb that balance? Introduce some kind of, stress.
That brings us straight to the Chatelier's principle. It's a cornerstone idea.
Explain that a bit.
Basically, if you stress a system that's happily sitting at equilibrium, maybe add more reactant, take away product, change the temperature,
Right.
the system doesn't just sit there. It actively shifts. It changes the balance in a way that counteracts, that minimizes the stress you just applied.
So it tries to get back to a comfortable state.
In a manner of speaking, yes. And a really direct example of this is the common ion effect.
Common ion. Okay, what's that about?
It's specifically about adding an ion that's already part of the equilibrium you're looking at.
Right. Let's make that concrete. Say acetic acid and water. That's vinegar, basically.
A weak acid, yep. So it sets up an equilibrium. CH3COH dissociates slightly into H plus and acetate ions, CH3COO.
Okay, equilibrium established. Now here's the nudge. What if we dissolve some sodium acetate in there?
Good example. Sodium acetate dissolves completely,
Yep.
right? It's a strong electrolyte.
So you suddenly get a flood of extra acetate ions.
Exactly. Acetate ions, the common ion. It's already part of that acetic acid equilibrium.
Ah, so that's the stress. Too much product.
Precisely. And Le Chatellier says the system will shift to relieve that stress. How?
It needs to use up those extra acetate ions. So it shifts backward to the left.
You got it. Back towards the undissociated acetic acid. CH3COO reacts with H plus to form more CH3COOH.
Which means less of the acetic acid stays ionized.
Correct. The ionization is suppressed.
Yeah.
And critically, because you're consuming H plus ions in that shift.
The concentration of H plus goes down.
Right. And lower H plus concentration means.
The pH goes up. The solution becomes less acidic.
Exactly. That's the common ion effect in action. A very neat internal adjustment.
And this whole pushback mechanism, this suppression, that's not just a neat trick, is it? It's fundamental to buffer solutions.
Absolutely fundamental. Buffers are one of the most important practical applications of this.
We see them everywhere, even if we don't realize it. Like you mentioned, our blood pH is tightly controlled.
Critically controlled, our enzymes would stop working otherwise. And it's buffers doing that heavy lifting. Same in gastric juices, many industrial processes too, cosmetics, textiles.
So what defines a buffer then? What makes it work?
Okay, a buffer solution has to contain two key components, a weak acid and its conjugate base, or alternatively, a weak base and its conjugate acid.
And in significant amounts, right? Not just trace levels.
Yes, that's crucial. You need decent concentrations of both. Now imagine you add a little bit of strong acid, H plus A, to this buffer.
Okay.
The conjugate base component of the buffer immediately reacts with that added H plus A. So if we stick with our acetic acid example, the acetate ions, CH3COO, react with the incoming H plus A.
Forming more acetic acid, the weak acid.
Exactly. You've taken a strong pH-crashing acid and converted it into a much milder weak acid. The pH barely budges.
And if you add a strong base, like OH.
Then the weak acid component of the buffer steps up. The acetic acid, CH3COH, reacts with the OH.
Producing acetate ions in water.
Right. Again, you've neutralized the strong base, turning it into the weak conjugate base in water. The pH jump is minimal.
So the takeaway is buffers are like chemical shock absorbers for pH changes.
That's a great analogy. They prevent those wild swings you'd see if you added the same acid or base to just plain water.
Is there a way to calculate or predict the pH of a buffer?
There is, and it's incredibly useful. The Henderson-Hasselbalch equation.
Ah, yes, that one.
It relates the pH of the buffer to the pKa of the weak acid and the ratio of the conjugate base to weak acid concentrations. pH equals pKas plus the log of base acid.
pH Tx plus log AHA.
Exactly. And notice, if the concentration of the conjugate base equals the concentration of the weak acid.
Then the ratio is 1 and the log of 1 is 0.
Right. So the pH simply equals the pKa. That's actually the point where the buffer is most effective at resisting changes in either direction.
Okay, that makes sense. What about actually making a buffer if I need one at, say, pH 5.0?
Good question. Practicality matters. First, you need to choose the right weak acid system. The key rule of thumb is that a buffer works best within about 1 pH unit of the weak acid's pK.
Why is that?
It comes back to that Henderson-Hasselbalch equation. That ratio of base acid needs to be between roughly 0.1 and 10 for the buffer to have significant capacity.
Because log pico 1 is -1 and log 10 is +1. So pH equals UCK -1.
Precisely. Outside that range, one of the components is too low in concentration to effectively neutralize incoming acid or base.
So step 1,
Oh.
pick a weak acid with a pK close to your target pH.
Exactly. If you wanted pH 9.5, you might look at hydrocyanic acid, pKa 9.31, or phenol, pKa 9.89.
Though maybe you'd prefer phenol over cyanide for safety reasons.
Generally, yes. Practical considerations like toxicity and stability are always important in the real lab.
Okay, so we've covered equilibrium, the common ion effect, and buffers. Let's shift gears a bit to another technique, titrations.
Titration's a classic analytical method, really powerful for finding unknown concentrations.
How do they work and what do they tell us?
Well, you're essentially reacting a solution of known concentration, the titrant, with a solution of unknown concentration until the reaction is just complete. You monitor the pH as you add the titrant, and plotting that gives you a titration curve.
And these curves look different depending on what you're titrating with.
Very different. Let's take a strong acid with a strong base, like HCl and NaOH.
Okay, starts acidic, so low pH.
Right. Then the pH rises slowly, then suddenly there's this incredibly steep, almost vertical jump in pH right around the equivalence point.
The equivalence point being where moles of acid equal moles of base.
Exactly. And for strong acid, strong base, that equivalence point is precisely at pH 7 bore 0. Because the products, like NaCl and water, don't affect the pH.
Makes sense. What about a weak acid with a strong base? Like our friend acetic acid with NaOH.
Okay, starts at a higher pH because acetic acid is weak. The initial rise is more gradual.
And you see that buffer region you mentioned earlier.
You absolutely do. Before the steep rise, the pH changes slowly because you're creating a buffer mixture of acetic acid and acetate. Then the steep part is shorter and less vertical than the strong case.
And the equivalence point? Still 7?
Nope, it's above pH 7. Why? Because at the equivalence point, all the acetic acid has been converted to acetate ions. Acetate is a weak base. It hydrolyzes water slightly to produce OH.
So the solution is slightly basic at equivalence. Clever.
It is. And conversely, for a strong acid with a weak base, like HCl and ammonia,
The starts basic, high pH curves down.
and the equivalence point is below pH 7, because you formed ammonium ions, NH4 plus plain, which is a weak acid, and hydrolyzes to produce H plus A.
Okay, these curves tell a detailed story. But in the lab, how do you know when you've hit that exact equivalence point? You can't always measure pH continuously,
Good point. That's where acid-base indicators come in.
like litmus paper or phenolphthalein.
Exactly. They are usually weak organic acids or bases themselves, and the key is that their undissociated form has a different color than their ionized form.
So they change color depending on the pH.
Right. Now, it's important to distinguish between the equivalence point, the theoretical point of complete reaction, and the endpoint.
The endpoint is just when you see the color change happen.
Precisely. And the trick is to choose an indicator whose color change range falls within that steep vertical part of the titration curve.
So the visual endpoint closely matches the actual equivalence point.
You got it. For that weak, acid-strong base titration ending above pH 7, phenolphthalein is great because it changes color between pH 8.3 and 10.
Right in that steep region.
But methyl red, which changes around pH 4 to 6, would be a terrible choice. It would change color way too early.
Fascinating. Even red cabbage juice can work, right?
Yeah, nature has its own indicators. It's pretty neat.
Okay, let's shift again. From pH and acids bases to solubility. We tend to think of things as either soluble or insoluble, but it's more of a spectrum, isn't it?
Definitely. Even things we call insoluble, like maybe silver chloride, actually dissolve a tiny, tiny bit. It's another equilibrium.
Solubility equilibrium. So how do we quantify that?
We use the solubility product constant, KSP.
KSP, okay.
For a slightly soluble ionic compound, like AgCl dissolving into Ag plus and Cl ions, AgCl solid in equilibrium with Ag plus aqueous and Cl aqueous,
Uh-huh.
the KSP is just the product of the concentrations of the dissolved ions, each raised to the power of their coefficient in the balanced equation. So for AgCl, KSP equals Ag plus Cl.
And the solid AgCl doesn't appear in the expression, right, because its concentration is constant.
Exactly. Solids and pure liquids don't feature in equilibrium constant expressions. And the key thing is a smaller KSP value generally means the compound is less soluble.
Okay, so KSP tells us how insoluble something is. Can we use it to calculate the actual amount that dissolves?
Yes, absolutely. We can calculate the molar solubility, which is the moles of the compound that dissolve per liter of solution to make it saturated.
Or just solubility in grams per liter?
Right. Using the KSP expression and some stoichiometry, you can find these values. For example, silver bromide, AgBr, has a really tiny KSP, about 7.7 by 1013.
Wow, that's small.
It is, and that corresponds to a molar solubility of only about 8.8 by 10 to 7 moles per liter. Barely anything dissolves.
Okay, so KSP relates to how much dissolves. How does this help us predict if a precipitate will actually form if we mix solutions?
Ah, that's where we compare KSP to the reaction quotient, Q.
Q again. We use that for gas equilibria too.
Same principle. You calculate Q using the initial concentrations of the ions you're mixing, plugged into the same expression as the KSP.
Okay, so Q tells us the state before equilibrium is reached.
Exactly. And then you compare.
If Q is less than KSP.
The solution is unsaturated, more could dissolve. No precipitate forms.
If Q equals KSP.
The solution is exactly saturated. It's at equilibrium, no net precipitation.
If Q is greater than KSP.
The solution is supersaturated. It's holding more ions than it should at equilibrium. A precipitate will form, crashing out ions until the concentrations drop back down so that Q equaled KSP again.
That makes sense. It's like the system trying to get back to that KSP balance. And why should we care about predicting precipitation beyond the lab?
Well, think about those kidney stones you mentioned earlier, often calcium oxalate.
Right.
Their formation is basically a precipitation reaction happening inside the body because the concentrations of calcium and oxalate ions exceed the KSP of calcium oxalate under those conditions. Understanding solubility helps explain and potentially prevent things like that.
Okay, so the KSP itself is key.
Yeah.
But are there other factors that can influence how much something dissolves beyond just its inherent KSP in pure water?
Oh, absolutely. Several important factors.
Like what?
Well, first, let's bring back the common ion effect.
Ah, it applies here too.
Definitely. If you tried to dissolve a slightly soluble salt, like our AgCl, in a solution that already contains either Ag plus or Cl ions.
From some other source, like silver nitrate or sodium chloride.
Exactly. That common ion will push the solubility equilibrium of AgCl back to the left.
Meaning less AgCl will dissolve.
Significantly less. AgCl is something like 500 times less soluble in a dilute silver nitrate solution than in pure water because of the extra Ag plus ions already present.
Wow. So the common ion effect suppresses solubility, just like it suppressed ionization for weak acids.
Same principle, different context. Another major factor is pH.
How does pH affect solubility?
It depends on the compound. Consider metal hydroxides like magnesium hydroxide, MgOH2, which is milk of magnesia. It's only slightly soluble.
Okay.
If you put it in an acidic solution, low pH, the H plus ions react with the OH ions produced by the dissolving MgOH2.
Removing the OH product.
Right. And by Le Chatelier, removing a product pulls the equilibrium to the right, dissolving more MgOH2.
So metal hydroxides are more soluble in acid.
Generally, yes. Conversely, they're less soluble in basic solutions because of the common ion effect of the added OH.
What about salts that don't contain hydroxide but maybe contain a basic anion, like fluoride F or sulfide S2?
Good question. Those salts, like barium fluoride, BAF2, or copper-2 sulfide, CuS, are also generally more soluble in acidic solutions.
Why is that?
Because the anion, F, S2, etc., is the conjugate base of a weak acid, HF, H2S. In acidic solution, H plus reacts with that basic anion,
Pulling the anion out of the solubility equilibrium.
Exactly. So again, the equilibrium shifts right, dissolving more of the solid salt.
This ties into teeth again, doesn't it? Hydroxyapatite in enamel?
Absolutely. It's a calcium phosphate salt. Phosphate is a basic anion. Acids produced by bacteria in the mouth can react with the phosphate.
Dissolving the enamel over time. Tooth decay.
Precisely. And that's why fluoride helps. It incorporates into the enamel as fluoroapatite, which is less soluble, especially in acid, than the original hydroxyapatite.
It's like armoring the tooth at a chemical level. Very
Yeah.
cool. Any other factors?
One more big one, complex ion formation.
Complex ions. What are those?
They consist of a central metal action bonded to one or more surrounding molecules or ions called ligands. Ammonia, NH3, or cyanide, CN, can act as ligands.
Okay, how does forming these affect solubility?
It can increase solubility dramatically. If you have a slightly soluble salt, say silver chloride again, AgCl,
Uh,
if you add something that forms a stable complex ion with a silver ion, like ammonia.
the Ag plus ions that dissolve from the AgCl get immediately snapped up by the ammonia to form a complex like AgNH3 2 plus N.
Exactly. This effectively removes the free Ag plus ions from the solution.
The Chevalier again. Removing product pulls the reaction right.
You got it. More AgCl dissolves to replace the Ag plus being used up in the complex. Sometimes this effect can increase solubility by many orders of magnitude.
Is there a visual example?
A classic one is copper 2 hydroxide, CuOH2. It's a pale blue precipitate, quite insoluble.
Okay.
But if you add excess ammonia solution, the precipitate completely disappears and you get this stunning deep blue solution.
Why?
Because the coppered ions have formed the stable tetramine copper 2 complex ion, CuNH342 plus I, which is soluble.
So complex formation can dissolve things that seem stubbornly insoluble.
Very effectively. The stability of these complex ions is measured by a formation constant, Kf. Large K means a very stable complex and usually a big boost in solubility.
Okay, common ions decrease solubility. pH can increase or decrease it depending on the salt. And complex ions generally increase it. That's a lot to juggle.
It shows that solubility isn't simple. It's dynamic and depends heavily on the conditions.
So how do chemists use all this knowledge in practice? Can we use these different solubilities to, say, separate ions from each other?
Absolutely. That's called fractional precipitation.
Fractional, because you precipitate things out in fractions one by one.
Exactly. You exploit the differences in their KSP values. Imagine you have a solution containing chloride ions, bromide ions, and iodide ions.
ClBr.
Okay. Now you start slowly adding a solution of silver nitrate, AgNO3. Silver forms slightly soluble salts with all three, AgCl, AgBr, and AgI.
But they have different KSP values.
Critically different. The AgI has the smallest KSP, meaning it's the least soluble. HBr is next, and AgCl is the most soluble of the three, though still not very soluble.
So as you add the silver nitrate, the KSP of AgI will be exceeded first.
Precisely. So silver iodide will precipitate out first. As you continue adding AgNO3, you'll reach the point where AgBr starts precipitating. Add even more, and eventually AgCl will come out.
So you can potentially separate them by carefully controlling the amount of silver nitrate added and filtering off the precipitates sequentially.
That's the principle. It requires careful control, but it works.
Does this tie into identifying unknown ions?
It's the basis for traditional qualitative analysis schemes. You'd have a mixture of unknown metal ions, and you'd add specific reagents under controlled conditions, like controlling pH or adding sulfide ions, to selectively precipitate groups of ions based on their solubility rules and KSP values.
Then you'd test the precipitates further to identify the specific ions.
Right, maybe using things like flame tests for characteristic colors like sodium's yellow or potassium's lilac. It's like chemical detective work using solubility.
Wow. Okay, so we've really covered a lot of ground, from the common ion effect influencing both weak acid ionization and solubility,
to the vital role of buffers in maintaining stable pH.
the insights we get from titration curves and indicators.
And then this whole complex world of solubility, KSP, predicting precipitation, and the factors like pH and complex ions that affect it.
It really shows how these equilibrium principles are interconnected and have such broad applications.
They really do. If you think about the bigger picture, these rules of chemical equilibrium, they're not just in textbooks, they govern so much.
Like water treatment.
Exactly. Ensuring heavy metals precipitate out, or how nutrients are available in soil, how medicines are formulated to dissolve correctly in the body.
Even geological formations over millennia.
It's fundamental. Understanding equilibrium gives you this incredible lens to see the invisible chemical forces shaping our world. From the microscopic scale of ions to macroscopic processes, it's the chemistry happening constantly, quietly, all around us.
So, thinking about all this, what stands out to you? How does understanding this intricate dance of equilibrium change the way you see everyday chemistry? We hope this deep dive has sparked some connections and given you a powerful new perspective.